An amorphous solid does not possess a well-defined arrangement and long-range molecular order. A glass is an optically transparent fusion product of inorganic materials that is cooled to a rigid state without crystallizing. Notice the difference between crystalline quartz, silicon dioxide, and non-crystalline quartz glass. Phase changes. Phase changes exist between the three states of matter, gas, liquid, and solid. If you go from a solid straight to a gas, it's referred to as sublimation. A solid becoming a liquid is melting. A liquid becoming a gas is vaporization. The reverse, a gas becoming a liquid, is condensation. A liquid becoming a solid is freezing, and a gas going straight to a solid is deposition. The equilibrium vapor pressure is the vapor pressure measured when a dynamic equilibrium exists between condensation and evaporation. All liquids have vapor pressure. It's a dynamic equilibrium. The rate of condensation equals the rate of evaporation. The molar heat of vaporization, delta H sub VAP, is the energy required to vaporize 1 mole of a liquid at its boiling point. If we look at a diagram of vapor pressure versus temperature, we notice that various liquids have various vapor pressures, and they are nonlinear. If we apply the Clausius-Clapeyron equation, the natural log of the pressure equals minus the heat of vaporization divided by the gas constant times the absolute temperature, we can plot the log of the pressure versus the reciprocal of the absolute temperature and get a nice straight line adherence. There are two forms of the Clausius-Clapeyron equation for calculation at two different temperatures. It's the natural logarithm of the ratio of the pressures equals the heat of vaporization divided by the gas constant times the difference in the reciprocal of the absolute temperatures. Either form of the equation will work. We'll demonstrate that in class. The boiling point is the temperature at which the equilibrium vapor pressure of a liquid is equal to the external pressure. Don't confuse the boiling point with the normal boiling point. The normal boiling point is the temperature at which a liquid boils when the external pressure is 1 atmosphere. Here's a table of molar heats of vaporization for some liquids. The critical temperature, T sub C, is the temperature above which the gas cannot be made to liquefy, no matter how great the applied pressure. The critical pressure, P sub C, is the minimum pressure that must be applied to bring about liquefaction at the critical temperature. Here is the critical phenomena of sulfur hexafluoride. Notice that if the temperature exceeds the critical temperature, the liquid totally disappears. There's no more meniscus. Solid-liquid equilibrium. The melting point of a solid, or the freezing point of a liquid, is the temperature at which the solid and the liquid phases coexist in equilibrium. Remember that melting and freezing are just the opposite, but the same amount of energy. The molar heat of fusion, delta H sub FUS, is the energy required to melt 1 mole of a solid substance at its freezing point. Here's a table of molar heats of fusion for some substances. This is a heating curve. It shows that if we take a solid and heat it to the equilibrium between the solid and the liquid, we get a plateau at the melting point. If we continue to heat now the liquid, we reach another plateau, which is the boiling point. The liquid and vapor are in equilibrium. Finally, point D, we take the liquid and totally vaporize it and heat it. Solid-gas equilibrium. Here the solid is directly in equilibrium with the gas. The molar heat of sublimation is the energy required to sublime 1 mole of solid. The heat of sublimation is equal to the heat of fusion plus the heat of vaporization. Here's a picture of iodine being sublimated and recondensed on the top surface that's being cooled. A phase diagram summarizes the conditions at which the substance exists as a solid, liquid, or gas. There is the solid region, the liquid region, and the vapor region. Where the lines intersect is called the triple point. For water, the triple point is 0.006 atmospheres and a temperature of 0.01 degrees Celsius. A more dramatic phase diagram is for carbon dioxide. The triple point for carbon dioxide exists at 5.2 atmospheres and negative 57 degrees Celsius. There's a picture of dry ice sublimating directly from the solid to the gaseous state.